So, in this part of the lecture we are going to use the treatment of the circular waveguide to the analysis of the circular cavity, which is nothing but the circular waveguide capped by two metallic plates at two z locations, okay. And we are going to find the resonant frequency of the circular cavity, the stored energy in the cavity, the power dissipated in the walls of the cavity, and thereby evaluate the Q factor of the cavity. So, let us draw the cavity. So, this is the Z, this is the Y, this is the X, this is phi, this is rho, the radius A of the cavity and the height D of the cavity. So, as we said, it is a section of the circular waveguide closed by conductors at z equal to 0 and z equal to a. So, therefore, it must be satisfying the boundary conditions at z equal to 0 and z equal to a, in addition to the boundary conditions for the circular waveguide, namely the vanishing of the tangential fields at rho is equal to a. So, the additional boundary conditions must be satisfied at this surface and at this surface. So, which means the tangential electric field must vanish at z equal to 0 and z equal to a. So, which means the tangential electric fields at z equal to 0 and z equal to a are E rho, and if I say so, they must both vanish at z equal to 0 and z equal to a. So, we will get, if we follow these principles, the Tm to Z modes, the corresponding psi function given by n p q Tm as Jn xn p rho by a, because nothing is disturbed along the rho direction, nothing is disturbed along the phi direction. So, it remains sin n phi cos n phi. However, we have a cos q pi z by d, which is equation 40. Cos q pi z by d corresponds to standing waves along the z directions. So, this form of function, whether it is sine or cos, is determined by exactly the same logic as we followed for the rectangular waveguide cavity, and I leave it up to you. Okay. So, we follow exactly the same reason that the tangential components of E has to vanish at z equal to 0 and z equal to d, and we come up with the appropriate sine or cos decomposition corresponding to this vanishing of the tangential electric fields at z equal to 0 and z equal to d. So, whatever wave function along the z direction satisfies this vanishing of the electric fields at z equal to 0 and z equal to d must be chosen, and this choice is exactly the same as in the rectangular waveguide, or follows the exactly the same principles as we did for the rectangular waveguide. So, n is equal to 0, 1, 2, p equal to 1, 2, 3, and q equal to 0, 1, 2. Similarly, the set of modes corresponding to the T to Z modes of the cavity Similarly, the T to Z modes of the cavity, the potential functions corresponding to the T to Z modes will be given by psi n p q T e as j n x n p dashed rho by a sin n phi cos n phi sin q pi z by d. Again, the choice of this sine function should be easy for you to find out, and I leave it up to you. So, n is 0, 1, 2, p equal to 1, 2, 3 and q equal to 1, 2, 3, because it is a sine function. So, the separation equation for the Tm So, the separation equation for the Tm and the TE mode becomes for the Tm mode we have x n p by a whole square, which is k rho square, plus k z square, which is q pi by d whole square equal to k square. So, this is nothing but k rho square plus k z square equal to k square. So, we call this equation 42. And for the T case, the same equation k rho square, sorry, it should be k rho square plus k z square equal to k square should yield x n p dashed by a whole square plus q pi by d whole square equal to k square, that is 43. Now, since k is equal to the familiar substituting k as twice pi f root of epsilon mu, we can solve for the resonant frequencies of the cavity from these two expressions. So, f r, the resonant frequency of the cavity corresponding to the NPQ mode or the NPQ TM mode is given by 1 by twice pi a root of epsilon mu root of x n p square plus q pi a by d whole square. We call this equation 44. We call this equation 44. And if R NPQ for the TE mode becomes 1 by twice pi a root of epsilon mu root of x n p dashed square plus q pi a by d whole square this becomes 45 corresponding to the NPQth TE mode. So, these two expressions yield the resonant frequencies of the cavity. Now, in order to find out the Q factor of the cavity, the quality factor of the cavity, we specialize to the TM010 mode. So, the quality factor of the dominant TM010 mode. Dominant for small values of the cavity height. So, we need to find out the fields, because we need to find out the energy stored. For that we need the fields, and we need the power dissipated on the walls, for which we need the fields. So, first of all we need to find out the psi function for the TM01 mode, for that we need to find out the psi function for the TM010 mode. So, the psi 010 TM2Z mode is given by J0 x 01 rho by A. Okay. So, uniform variation, so it is 0, n is 0, that means uniform variation along the phi direction. The azimuthal variation of the field is uniform, and the distribution of the field is also uniform along the z direction, because there also we have q as 0. So, only p is 1. So, therefore, the psi function becomes J0 x01 rho by A, and from there we can find out all the field components. From 21 we have Ez given by 1 by j omega epsilon del square del z square plus k square psi, that is k square by j omega epsilon J0 x01 rho by A. We call this as equation 47. So, we note that del z is 0, because there is no z variation in 46. So, del z, this term is 0. Then from equation 19 we can find out the magnetic field component H phi, that is del psi minus del psi del rho, that is given by minus del rho of J0 x01 rho by A, that is given by x01 by A J1 x01 rho by A, which is 48. So, we know Ez and we know H phi. Okay. Now, we can calculate the stored energy in the cavity. Please verify what happens to the other field components. Please verify that yourself. Why we have considered only Ez and H phi. So, the stored energy in the cavity is given by W is equal to twice W E bar, that is epsilon triple integral mod E square dV that is given by epsilon rho equal to 0 to a. So, the volume integral phi equal to 0 to 2 pi and z equal to 0 to d mod E z square rho d rho d phi d z. Okay. So, W becomes equal to epsilon k to the power 4 omega square so that becomes epsilon k to the power 4 divided by omega square epsilon square 2 pi d 0 to a rho j 0 square x 0 1 rho by a d rho, that is equal to pi k to the power 4 d s square by omega square epsilon j 1 square x 0 1. Let us call this equation number 49, and this happens since 0 to a rho j 0 square x 0 1 rho by a d rho is equal to a square by 2 j 1 square x 0 1. Okay. So, here we note that del del z equal to 0 and E rho equal to E phi equal to 0. So, that is why this E becomes equal to Ez, or mod E square becomes equal to mod Ez square. Okay. So, now in order to find out the power dissipated in the conducting walls of the cavity, we need to find the corresponding tangential magnetic fields on the walls of the cavity. So, we go to equation number 19 for the TM2Z modes, and from 19 we obtain H rho as 1 by rho del psi del phi is 0, because psi has no phi variation. Okay, again right here psi 0 1 0, Tm was J 0 x 0 1 rho by A, it has no phi variation. So, this is 0, H rho is 0, we have H phi as x 0 1 by A, J 1 x 0 1 rho by A, that is from equation 48. And Hz is 0. So, therefore, mod H square is H phi square, which is x 0 1 by A whole square J 1 square x 0 1 rho by A. So, power dissipated in the conducting walls is given by P d bar is R surface integral mod H square ds, that is R x 0 1 by A whole square phi is equal to 0 to 2 pi z equal to 0 to d, that is over the curved surface area of the cylinder. So, J 1 square x 0 1 A by A because rho is equal to A, we are finding out the power dissipated at rho equal to A, then A d phi dz plus 2 times rho equal to 0 to A phi equal to 0 to 2 pi corresponding to the 2 end caps. So, this term corresponds to the 2 end caps, the power dissipated on the 2 end caps of the cylindrical cavity. So, that will be equal to J1 square x01 rho by A rho d rho d phi. That is equal to R x01 by A whole square times 2 pi A d J1 square x01 plus 2 0 to A rho J1 square x01 rho by A d rho. And that eventually turns out to be R x01 by A whole square 2 pi A d plus A times J1 square x01, that is equation 50. Where R is the intrinsic wave resistance of the metal walls. So, R is the intrinsic wave resistance of the metal walls. Metal walls. So, now the Q of the cavity is given by omega w by P d bar, which we have already found out. That is equal to omega pi k to the power 4 dA square by omega square epsilon J1 square x01 times 1 by R x01 by A whole square 2 pi A d plus A J1 square x01. And then that becomes on simplification k to the power 4 dA cube divided by 2 omega epsilon R x 0 1 whole square d plus a. Call this as equation 51. So, this finally yields the expression of the Q factor of the cylindrical cavity, which is very important for characterizing the cavity in terms of the stored energy and the power dissipated on the cylindrical cavity walls together with the end caps. So, this completes our treatment of the cylindrical cavity and the entire chapter on cylindrical wave functions, circular waveguide and cylindrical cavity. Thank you.